And start talking about rocket science.
Good.
So thank you everyone for showing up. Thank you for being patient with these seemingly more difficult technical issues than it takes to put things into space, which is Zoom. Today's seminar is on spacecraft embedded systems engineering. It is okay if you have no idea what that is. I'm hoping I can explain that in the next 45 minutes, and I believe I can do it. I'm also a nerd, so that's why I threw a little tagline on there, or how I stopped worrying and love cosmic bit flips. I'll explain that as well. That's a good old reference to Dr. Strangelove. My name is Emile Semmes, and let's get started. So one of the things I've done only a handful of seminars, but I want to make sure that there's an actual goal for this. This isn't just about me blabbing, although I can do that for a very long time. The whole point of this is that I'm hoping you can understand what spacecraft systems engineering is about. Well, not just engineering, but embedded systems, but understand why there's a specific aspect of it and the kind of problems that we experience when we're developing things to go into space and how we solve them. Because they're really difficult, but we actually have solutions for them. And also just not just to tell you about how these things are done, but also give you a pathway to like see how you yourselves can be a part of this. It's, it just takes training, some learning, and some, of course, a little bit of dedication. Well, a lot of dedication, but this is a field that you can get into. So again, my name is Emile Semmes. Well, as of a couple of days ago, I am now a software manager at a company called Leo Stella. It's actually a local satellite manufacturer in the area, actually up in Tukwila. But prior to that, I've done a couple of other space-related I've had a couple of space-related positions. Previous to this, I was working as a principal spacecraft engineer for a satellite communications firm in the Bay Area called Astronis. They make what you call geosynchronous, geostationary satellites that beam down the internet, basically. So their company, their intent was to help nations, like full-on nations, deliver internet to them, because sometimes it was easier and faster to get them internet through space than the ground and other forms. Prior to that, I was a lead software engineer at Blue Origin. You guys might know him. That's that rich dude that lives not too far away from here, makes spacecraft that go up to space and come back down. He's put a bunch of celebrities in space. So I worked for him a couple of years ago as well. I was a lead software engineer for two of their rocket engines there. One was an engine that would help you land on the moon. Another one was to help you get to the moon. So, and then prior to that, I mean, I've been doing this for about 25 years, but my other big gig was working at that small company called Microsoft. I did like some random stuff on the Xbox. Like no one cares about that stuff. So what is spacecraft embedded systems engineering? Which, sorry, I actually gave the name of this, I presented it earlier as spacecraft software engineering. That was a misnomer on my part. It's kind of in La La Land when I wrote it, but I meant spacecraft embedded system engineering because that's what I am. I'm an embedded systems software engineer. So there's a lot of stuff to unpack with that, but just to go off the bullet points here, spacecraft embedded system engineering is a lot of stuff. It's basically the field of designing the brains behind the electronics that go into space. So, and that's for satellites and rocket engines and other spacefaring equipment, things. So basically, we have to have a specific focus on the kinds of challenges we need to overcome to get to space safely, without blowing up, without killing people, stay in space without degrading. And then also, if we're going to land somewhere, whether it's back on Earth or the moon or Mars or what have you, there's a lot of new technology and algorithms that we have to employ to actually get there. But the other thing about space is, well, space is really deadly and dangerous. We're creatures of Earth. We're not really meant to go into space. So there's a lot of different protections that we have to do just for humans just to get into space, but also for our electronics. Because the moment we leave our atmosphere and magnetosphere, there's all these new radiation aspects that we have to deal with. And that's really the number one thing that makes designing electronics and software for space different. We have to think about radiation. So as I mentioned, this is about, satellites and rocket engines and things like that. But just to make sure you kind of understand what they are, so and what they're used for. A lot of, I think most folks understand or know what GPS is. GPS is a satellite system where it has a number of satellites in space orbiting the Earth. Well, actually in geostationary orbit. I'm looking to see if any of my friends jumped on, but I believe it's geostationary, meaning you put it up in orbit over Earth, and it just stays there in the same position. So even as the Earth rotates, the satellite stays in the same position where it was launched, and it stays there. And we use that to provide positions, a global positioning system. And I was saying earlier, one of the other projects or one of the companies I work for was a communication satellites organization, and they also work in the same way. We put it in space, it stays there, and we beam data up to it, and then it beams data back down to a different location. Other things you may have heard like that are that other dude, Elon Musk, he's got his company called SpaceX, and they have Starlink. Same concept, but those satellites are actually lower in altitude. So we have GPS, it's like, I forget, was it 32,000 kilometers above the Earth's surface? Starlink is a little bit lower. I forget how many kilometers it is, but those satellites actually don't stay in the same position with Earth. They continuously fly around. So, and because there's so many of them, those satellites, as they pass over, you basically transfer data to each one, and the next one comes by, you now connect to that one. And all the engineering behind that makes it seem seamless so you don't lose internet constantly. When it comes to software, the software that runs on those satellites have to make sure that they're making sure that each satellite is in the right position. Even if it's moving constantly, it's still intentional. It has to make sure that it can check and make sure it's doing okay. Because again, it's in space. No one's going to drive a truck up there and, can't plug things into it. It's got to be fully autonomous, being fully automatically controlled. And so the software on there has to make sure that it's always checking, making sure it's okay, making sure that if something goes bad, it knows how to handle it automatically, and let people know if it's too difficult for it to solve on its own, that something bad is happening. And even if it can't, send just a whole bunch of raw data so people down on the ground could say, oh, that satellite is actually spinning around the wrong direction. We need to fix it. So that's kind of the basic aspect of how software and how those kind of satellites work. By the way, if you have any questions, please raise your hand in person or on Zoom. I am fully okay with you. Like, if you have any questions or interruptions, completely work fine with me. Okay, so the next part is other aspect of my other part of my career that I also have knowledge with is rocket engines. So as I mentioned earlier, I helped. Well, I didn't help. I actually led the team to write the software that to create engines to help people land on the moon. And yes, we have landed on the moon before. That is not fake. It's not staged. It's possible. We did it multiple times. Other countries have done it too. I wouldn't have been employed if it was not real. But anyway, the difference between the software that runs on a satellite and a rocket engine is that, it's got to make it go, right? Satellites do go, but not as quickly and not as often, they don't have to worry about a lot of different types of fuel and moving it from the ground to space. Rocket engines do have to calculate that. And to simplify it, just think about your car engine, right? The same concept, right? Cars have fuel and air. You mix them together with some spark, and it makes I'm talking about combustion engines, not EVs. Who cares about EVs? Those no one wants those anyway. But a rocket engine works the same way. You've got fuel and some ignition, and it makes fire come out, as you see in the pictures here. It's just a lot more fire, and the fire is constant until you turn it off. And hopefully when you turn it off, you're in space and not still on the ground. So the software that we write for that has to think about the mixture of that fuel and also get that one spark, because we don't spark a lot with engines. Just hit it once and then it turns on, and boom, explosion happens, and hopefully it's going the right direction so you go up, not all over the place. The difference with that is that we have to do it really, really fast because we have to work at the speed of physics and chemistry to make these really, really quick adjustments so that we can adjust the power. And if something really bad happens, we could shut the whole thing off so not everyone explodes. Perfect. Again, you don't have to be fully on top of this, but perfect example was at Blue Origin. they had a launch, one of their most recent launches. Everything's fine, everything's gonna be going fine, but there was one mishap that happened. And due to my coworkers, because I used to work there, they wrote something in the code to say, oh my God, something bad is about to happen, shut it down. And so although I don't think it exploded, but that's the kind of software you have to write, something that responds quickly, can put things in a state where things can be safely recovered and no one dies. We don't have a whole bunch of stuff exploding. So so we really are what we call it safety critical design in software and hardware. Again,
liquid oxygen to fuel, what are they using?
we do. It kind of just depends on the company's direction. Liquid LOX is used in I can't remember which engines, but yeah, Blue Origin uses them. SpaceX, ULA, a lot of companies still use liquid oxygen.
Do they even use a hydrogen oxygen mix or would that be-
Yes. Yeah. No, a lot of them still use that. Yeah. Yeah. Yeah.
That what happened with you remember NASA?
Which one?
The
Are you talking about the
back
Challenger?
in the Challenger?
Yeah.
I don't know, back in maybe that night, the one that went straight,
It blew up?
It blew up with the
That
seven
was
astronauts on it.
called O-rings.
Yeah, the O-ring one. Yeah.
They were defective.
Yep. Yep. That was
O-ring, so that was
neither hardware nor software. It was like a bad seal. So the fuel, like, do you remember? I don't remember it.
Was the problem with
I
the
know
quality
what happened,
assurance?
'cause I watched them.
What happened with those O-rings where they were not able to stand up to the temperature
Yep.
developed the night before?
Mm.
And there were micro fractures in those O-rings.
Mhm.
Now, when they had passed the original QA, they looked just fine because nobody accounted for that temperature drop that happened the night before.
Mhm.
Micro fractures, nobody saw them. Nobody really checked in depth. It was all good to go. They couldn't withstand the force when they ignited them.
Yep. Yep. So yes, safety critical planning, fault tree analysis, fault hazard analysis, just simulation, even looking at, I'm not really going to talk a lot about temperature, but those are other aspects. Just of course, temperature doesn't directly impact software, but when it comes to the electronics that we choose to control and orient and maneuver our engines and satellites, that is also one of the highest criteria, one of the other parameters we look at. Can it handle the extreme cold in space? Can it handle also the extreme heat? Because we don't have the ozone, we don't have the atmosphere to prevent the heat of the sun when things are facing it to manage it. So everything is really different out there. So, okay, let's see, next page. So, like I said, I'm more of a software engineer, but I'm also, also should have said I have a degree in electrical engineering as well. That's really my degree. I use software to communicate with electronics, so that's why, actually, I'm going to get back to that, but that's what makes me an embedded systems engineer. So the concept, the terminology embedded systems means you have a piece of electronics that does a very specific thing. So for instance, your computers, your cell phones, you wouldn't call those embedded systems because they do everything, the general purpose. An embedded system would be like a remote control. It has, there's a processor on here, there's probably some code that's running on it, and it does a thing, which is to drive you nuts with a whole bunch of buttons that don't make any sense, but at least it does that one thing. That's what an embedded system does, a specific thing. In order to reliably execute its behavior and in order to do the thing that you wanted it to do, typically we use some of the most basic programming languages. The core ones have been around since like the 60s and probably older, and that's C and C++. I threw on Rust because it's kind of like my jam. That's the newer language that's popping up nowadays. It's also very, very good at making sure that what you write does what you expect it to do, but also gives you like that very, very tight control. So again, like I was saying, engines, you have to respond very, very quickly in milliseconds or faster. You want to be able to have a language that can interpret your design ideas so you can handle those kind of really risky situations, handle them very quickly. High performance, high reliability. In addition to just writing the code, because just some random coder up the street, I mean, they might be good at this, but there's a whole aspect of the philosophy around how you software engineer. And that's also testing. I'm trying to see if any of my buddies are on right now, because no, they're not. Testing is also a very, 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 very important aspect of software development, any kind of engineering when it comes to space. Because, well, you should be able to prove that it's going to do what you expect it to do. Also because we can't exactly test in space yet. We don't have space stations that allow us to actually build, design, and test and code all the engines and satellites in space. We do it on the ground, and then we put it up there, and fingers crossed it works. But fingers crossed isn't good enough, so we do a lot of testing and simulation. And then and especially in the simulation side, we think about and we use a lot of the data that we've retrieved from previous satellites about the environment out there. So in other words, what kind of radiation are we experiencing? What kind of temperature change are we experiencing? What happens at different altitudes? Those are the kind of things that we use to even not just write software, but the whole aspect of that. And like I said earlier, space is a very hostile environment. It literally will kill you. Besides, I mean, of course, if you have to be out there in spacesuits, because if you just took a rocket up to space and just jumped out the airlock, you're dead because you'll freeze to death. We can't handle the temperature. But the aspects for electronics, like I said earlier, is radiation. And there's different parts of our magnetosphere, the outer parts of our atmosphere, inner and outer parts of our atmosphere that actually impact how electronics work. And each one has a different kind of behavior. As you're closer to the Earth, you have to deal with particles. So just think like atoms that will bombard and hit a processor or memory or any kind of electronics, even transistors, power circuits, anything that's on your electronics, and could cause it to explode. Not a massive fire, but it'll just basically change. It changes the way that the atoms communicate with each other, the way that the electrons, the data, the power, the current, and the voltage can appear to each other, which could create these unforeseen consequences and do horrible things to it. And then as you get further and further away, it's not as bad. You're not dealing with these bullets of electronic death. Instead, you're dealing with like a drizzle of acid rain, if you want to use that kind of like mildly acid, kind of like it just rolls off and you could just wipe away. But after a while, you get this total ionization dose. That's what they call it, not acid rain in space. That slowly eats away at the way that things perform. And so those are all the things we have to think about depending on where we're putting our satellites. For instance, if we're just trying to launch something if we're just doing some joyriding with New Shepard at Blue Origin, and just want to get up to space and see, hey, yeah, the Earth is round. We have to deal with some heavy ion stuff. But if we're trying to go to the moon or beyond, we have to deal with this total ionization dosage. Again, that's the slow, constant burn, the slow, constant eating away of your electronic system. It's inevitable. It's just going to happen. And so we do things to kind of defeat that mechanically, like we'll use lead and thicker materials. But that only gets you so far. Also, it makes things heavy, and putting heavy things in space is expensive. A few $1 million a launch. Don't want to spend all that money launching heavy things in space. So then we have to add things to the hardware and the software to detect when things are going bad and even fix them. Perfect example. Oh, actually, did I put it in here? Oh, no, I didn't. Oh, there it is. I'll just skip ahead. The perfect example that shows one of the difficulties of when you send objects into space that are eventually getting hit by that total ionization dose is the Voyager 1. This has been sent out in space since what, the 60s. It's been in space for 46 years. I can't do that math right now. I'm not a mathematician, just a rocket scientist. But this has been out there for so long with technology that is so old. We're still using blueprints to figure out what's going on. We didn't even have, like, most of the tools that we use nowadays didn't exist, but it's been out in space for such a long time that total ionization dose has changed the behavior of the electronics that are on it. And so what's happening, it's literally sending us gibberish. It's just, instead of sending us data like, hey, I'm still out here, hey, I'm still alive, and look at all this cool stuff I see, it's just blah, 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 blah. So, and it's expected, actually it was expected a very long time for this not to even last this long. But because we have better understanding of how radiation impacts things, we're able to actually kind of kick it, we're literally kickstarting it to kind of get it to recover again. So those are just some of the issues, some of the horrible aspects that you have to deal with and think about when you're designing a system that goes into space. Any questions so far?
The ionization dose, that's the cosmic rays and the gamma rays.
Well, yes, it's all the things. Because remember, once, especially for an interplanetary, interstellar, I think it's now interstellar, basically, because we're out of the solar system. For the Voyager, you're dealing with solar flares and gamma rays and X-rays and all the radiation. So every single different type of particle, random electrons just flying all over the place, protons flying all over the place, that hit it, that aren't being filtered by anything. Like I said, everything within Earth's magnetosphere, little bit of protection against stuff, but once you get out there, now you're dealing with galactic radiation. Things are just particles that survived random planetary bodies that may have absorbed all those horrible things, but now you're dealing with the vacuum, which means things once they're out there, just flowing, not really degrading that much. You just got random radiation and electrons and protons hitting it. So yes, all those things. So let me get to the cosmic bit flips since that's part of the tagline. So core computing that we use nowadays they're binary computers, right? Sure, you can write code and looks like English or what have you. Everything gets compiled down to a 0 and a 1 on a processor. And that is exactly how communication shares data amongst itself inside the processor, how it executes instructions, how it performs the commands, performs behavior that everyone spends their months and weekends. Well, that's kind of weird. Spends a lot of time writing the code and testing it. It still comes down to those zeros and ones. And radiation doesn't care how hard you protected everything. All you need is a single proton or some random electron that can come in there, get through your lead protection and just flip that one bit. And in the world of in the digital world, the difference between a 0 and 1 is, well, it's that significant because there's no 0.5s or 0.1s. It's either true or false. So if you had something and you weren't expecting a false, and instead now you get a true, which is a 1. So 0 is false, 1 is true. Your code could be executing a question that says, hey, can I still see the Earth? And you can have some random electron or random proton hit it, and it says, instead of the reality, which is, yes, I can still see the Earth, it could say, no, I don't, which can cascade into other behavior that satellite or the rocket engine was expecting to do. So if it thinks it can't see the Earth anymore, it might trigger a new set of behaviors, not unplanned, but it's an if-else statement. So it's either this, then do that, dichotomous. If you see Earth, you're good. If you don't see Earth, then it could say, rotate the satellite until you see Earth. And that might be a lot of operations. And it doesn't even know that it got hit by radiation. So that is a thing. We have to write code that could think about those potential problems, or we call them faults, to fix it. But we're always thinking about bit flips, literally losing sleep because I think about bit flips because the ramifications could be absolutely disastrous. And like I said, yes, it's a 0-1, but it could create this new behavior. It could execute behavior that we programmed, but we didn't expect to occur. That's what we call unintended consequences, but I forget the actual technical term for that. But it will cause it to do something totally different. So, and like I was mentioning earlier with the Voyager spacecraft, it's gone, what is it, 163 astronomical units away from the Earth, moving at 37,000 meters per second or kilometers per second. Yeah, it's pretty significant that one mistake is now causing it to perform in a completely unintended way by sending gibberish, and that's this. Let me see if I can pull up this link actually, because this website is pretty interesting. Just to kind of.
How far from the AU from Earth now?
I'll tell you in a second, because this should show it. That's 15 billion miles away. That's how far away Voyager 1 is from the Earth.
So it's through the Kuiper Belt, and it's probably the Oort Cloud.
I don't know that part. I'm
How
not
many
that.
miles is it?
15 billion. Yeah. Yeah. So yeah, it's moving, sorry, not meters per second. So it's not that fast. It's just 37,000 miles per hour. So, let's switch this. So 60,000, I can already say that. Yeah. So 63,000 kilometers per hour, 24 billion kilometers away from Earth.
Is Voyager 1,
This is Voyager 1,
you said 24 billion miles away?
24 billion kilometers. I just did the conversion between miles and kilometers. So
15 billion would be
24
37 kilometers.
15 billion miles is 24 billion kilometers. Yeah, I'm not testing you.
No.
It's okay. It's changing anyway, so
Oh.
you'll be fine. No one's going to go out to see it anytime soon. It's been going out for, like I said, 40 something years.
When I write about it later, I want to make sure I'm writing what I know what I'm talking about.
Oh, well, I believe I can share the link to this, and so you'll get the I'll make sure that you see the you'll have the link, so you can always go here. Yeah. So so like I said, we have all these really difficult things we have to deal with, but there are solutions. There are ways we can actually make sure that the code, the software running on there will do what we expect it to do, or at least have an idea of how it's going to behave. So if things go bad, we have a way to say, maybe we can restart it, or maybe we can get it to correct ourselves. So what that means, what that process we call is radiation hardening. And it happens in different ways. To be honest with you, not so much in software. It's usually based upon the electronics that we pick. We pick things that have different the ways that they're manufactured actually protects it, will make something what we call rad hardened, or sometimes will be more radiation tolerant. So it'll handle it, but at least it may not stop it, but it can at least absorb some of the impacts and at least let us know something bad is happening. And then they'll give us the ability to detect an error. And then the software will check to see if that error has been detected and then do something about it. Sometimes it can actually correct it. So again, remember, we have zeros and ones. It could be that critical if we're expecting a 0, but we get a 1. If it's not that big of a deal, or that the radiation, like if the whole thing didn't explode, that's why we're seeing weird numbers like that. If it's just a single flip between a 0 and 1, our software can say, oh, that doesn't sound right because I checked other parts of hardware and we expected it to be a 1. Therefore, I could either correct it, call error correction codes, or we could just say, screw it, and just reset the whole thing. Those are pretty extreme. There are other techniques we could maybe just say, well, let me compare it against some other part of the hardware. Do these two numbers match up? And if they don't, we're really smart, we'll take another one. So we'll usually take 3 inputs and then compare, and if we get at least 2 of the 3, because majority rules, it's democratic in space, we'll say, okay, well, that one is off. That one, we don't believe that one because we don't have a consensus. So we'll pick the solution that the other 2 came up with. So that's another way we can rad harden the software and rad harden the hardware. So yeah, that kind of gets into that's all 3 of the bullet points. So again, we can pick electronics that are smart enough to self-identify when something's going wrong on a single part. Sometimes we'll use multiple parts, a redundant system, to say, okay, we need to get at least 2 things to say the same thing about the same kind of expectations. And if those 2 match up, then we have a high level of confidence that not everything went bad. There's some other use cases where NASA has even suggested you actually kind of do like a blind development where you have almost 2 teams of people try to solve the problem, but they don't know what each other is doing, which means now you have, instead of someone saying, well, I'm going to skin the cat from top to bottom, the other one's like, well, we're going to skin the cat from left to right, but they're still going to get the same answer. So that means the way that like if radiation hit the sideways cat's shaving wrong, but the up and down, I'm sorry about my analogies, but it's the fact that we have 2 different behaviors, 2 different ways to get to the same solution, means that radiation is not going to have the same impact. It's not going to fall, it's not going to appear the same way. And so that's another way where you can just get away with having two systems and not have something that's a arbiter, a voter, or something that can say, no, this is it. Do you want to say something? Oh.
Yeah, so when you're talking about the like error detection, is this a situation where like a system would get a 1 or a 0,
Mhm.
recognize that that's not what it was expecting and like retest itself? Or do you have to rely on other systems to confirm or reject the original system's finding?
I'm going to give you a really engineering answer, which drives people nuts.
Okay,
It depends.
okay,
And also depends on the scope. Like, what do you consider a system? But just to not be obnoxious about it, usually we have ECC error checking, error correction codes, and usually that's on a processor, a single processor. Technically, inside the processor is a different system, a different unit, but there's an expectation that the behavior is that you have this thing that's constantly checking the values, and it is a separate thing. It's physically separate. And even on the little chip itself, it's still physically separate and it's far enough away where, I mean, you don't have radiation particles you can't see them. So more than likely, if it's going to hit one part of the chip, it's not going to hit the other part. So it's separate and isolated. So if it hits a piece of memory, the thing that's checking the data is not close to it. And it says, well, wait a second, I expected to see the value 6, and instead I saw a 4, which meant a bit flip occurred somewhere else. And actually, that's not right. No, that's true. It's whatever. It expected that one thing, and because it expected it, it could say, "Well, I know that it was off by just a single bit, a single value," and it could immediately correct it on the fly. So no one needs to get in there. You don't have to have another piece of code that actually goes in there and is checking because it already happened. It'll just inform us and say, "Hey, something weird just happened," and we can keep account of it. In space and radiation, these radiation environments, sometimes they happen so often that it's like there's no point of us actually trying to write code to always fix it. So they use a piece of electronics, another piece of hardware to do it because it's faster, more reliable, very specific, and it'll just do it much faster than code could do it. I feel like there's a second part to your question. What was that? Was it? Okay, go ahead.
I like her.
I can
So-
just, oh, I'm sorry.
Okay, no, go ahead. Go ahead. Yeah.
So is there only a problem with, so you said the zeros is fault? Zeros is fault?
No.
No?
No, it's just data. In binary, or in most computing nowadays, I say most because there's quantum computers, and I'm not even going to touch that. But the way that all computers nowadays work, again, excluding quantum computers, is they work in binary. So it's either 0 or 1. There's no bad or good. It's just how you define things. Like for instance, so the number 2 in binary, like 2, we call that decimal. In binary is a 1 and a 0. Sorry, it's
It's a base 2 number
a base.
system.
Yes,
So
right.
you count 0, 1, and 0, 1,
Right,
0, 1, 0,
right.
base 2.
And so we use a combination of zeros and ones to help translate them into larger numbers, and then eventually characters and letters and so on, and images and so on.
So if it's a 0, you try to get to 1, if it's 1, you try to go to 2.
No,
No?
it just is. It's just data.
Is it,
A zero is a 0,
okay,
and a 1 is a 1, and they're just the building blocks. Look at like that. They're like the atoms, the building blocks of data that computers use to process things and even to execute the program. So there's no good or bad to a 0 or 1. It's just when we say data, it just means it's identification. It's the thing. It's
kind of like if you were to play a game, you're pressing left, right,
Yeah.
input a code. Sort of thing.
yeah, exactly. So like left, right, up, down, those are four values. We consider a 4-bit value because you could have 0, 0 could be left, 0, 1 could be right, 1, 0 could be an up, and a 0, 1 or a 1, 1 could be a down or something like that.
Or like, so left, right, like left 0, right's 1.
Yeah.
Like left, right equals like you doing the top of numbers like that in a way that equals like it equals something.
Right. Yeah. It's just the most. Yeah. So think of like binary as the the elements like the protons and electrons, like the atom of a computer is the smallest value, the smallest thing. Okay, I know there's string theory and a whole bunch of, but it's not getting to that. But it's the smallest possible thing that you can use to identify data in a digital environment. So yeah, so 0 is not necessarily a bad thing, and 1 isn't a good thing. It's just how I identify things.
But I've got.
Oh no, keep on going. Was it about I think,
The zeros and one, didn't you say zeros are false and ones are true?
yes.
Meaning,
Oh, it doesn't, but it doesn't mean there's no emotion so attached to
Oh.
it. It's just 0. It's just one of the ways we enumerate value to things. So traditionally we say 0 is false, but not false as in a bad thing like
oh,
false or fake.
okay.
It just means when you're doing it the most lowest level comparison in a
Oh.
binary world, true and false, 0 and 1. As you add more context and more purpose to the functions you want it to do, that true false can say like, well, it's a comparison. Let's say, is 10 greater than 9? In the binary world, you would use an if statement or a compare statement, and it would say, is 10 greater than 9? The value is true.
Hmm.
But then you could switch the numbers around. Is 9 greater than 10? Then the answer is false because it's a response, it's a result. It's being used as a result to a comparison. Yeah, so it's just an identifier. It just says 0, 0, 1 is 1. Traditionally, we associate just a 0 with a false and a 1 with a true. And that's in a single bit, like only just that one value, 0 and 1.
Single bit.
Yeah, and then we can add more of those zeros and ones in sequence. So that's why sometimes you'll see like the Matrix, or I mean, not the Matrix has like really weird glyphs and stuff. But if you were to trick your computer to something bad, you would see like just 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0. All that's binary, and that could translate into help me, I'm falling apart. But you have to run it against kind of like a decoder ring. So you take a group of those numbers, and those, like let's say you take 8 of those numbers at a time. It's called a bit, or 8-bit, or a byte, sorry. You take 8 of those values at a time, and then you translate that to something else. You say like this 0, 1, 1, 0, 0, 1, 1, 1, 0 is equivalent to the letter A. So
It's like Braille, but for a computer.
there you go.
Where
Yeah.
like you feel the bumps on the Braille, those are just like
Mhm.
differently rearranged. So it's kind of like you're just rearranging themselves. So many combinations with so many zeros, ones with that many spaces.
Yep. It's like the alphabet. I want to move on quickly, but I think that's probably the best way to think about like alphabet. Like the letter T doesn't mean squat to you. But when you say THE, it's like, oh, that's it means it has much more context. Like 0 typically and 1 doesn't mean anything without the understanding of the next thing. Like you can't just always just look at a 0 and 1 and say, oh, I know exactly what that means. You have to apply something to it. So it's also the building block of numbers and characters and letters and images when it comes to computing.
So you're just playing around with it till you get it to where you want it to be, like you were saying, with the codes and all that.
Yes. Yep. Yep.
Okay.
Okay. Got a quick one before we go on?
So if I've got a probe,
Yeah.
it's out ready to enter the Kuiper belt.
Yeah.
And it tells me something's wrong, this isn't right. How does it transmit that information back to you? With standard radio waves? How does it transmit? So those are gonna travel slow, 763 miles an hour. This can take a long time to get back there.
Yeah, it's like, was it a couple of days or something like that? Or no, almost a full day to send it back. It just depends on the radio that they're using.
So are they taking any steps to actually infuse AI into this onboard technology?
No, it's too late. It's already fixed. Those processors were designed back in the 40s. There's no way they might use AI in the ground to help predict or maybe help analyze the data. But more than likely what's happening is that they're looking, as they're getting this gibberish back, they're thinking, what are the possible reasons why this could be happening? And they're looking at, and maybe there's some sense in it, and sometimes there isn't. And it's not just what we're receiving, it's what we can send back to it. And hopefully it'll respond to it. So one of the things they're probably doing, because the safest thing to do is just try to figure out what the problem is before just saying, forget it and reset it. because that's a really dangerous thing. It's like if you're driving your car down the street and you're like, you see smoke come out your car, instead of just pulling to the side of the road, you're like, screw it, take your key out of the ignition, just shut the car off. That's really dangerous. You don't want to do that. You usually want to turn your signal on, find a safe space to pull over to the side of the road, slow down, turn the key off, put the car in park, turn the key, all those things first. So that's what they're doing with these interstellar probes, is they really want to make sure that there's a way to recover, because if they just pull the plug on it, it may never recover. And now you got this floating object out there that's going to go around, and then some crazy old alien intelligence is going to take it over, call itself Vega, and come back to the Earth and destroy us all. We don't want that to happen. So, so that's why they're waiting for. That's why they're just paying attention to all that data to come back and say, like, maybe there's something recoverable from this. And then once they figure out what that recoverability is, then they'll send a command to it, and hopefully it'll be still aware enough to respond to that command and then execute that behavior. So that's why they're taking their time with that. And yeah, if they use AI to do it, that's all happening here. They're not doing it out there. That technology didn't exist back then. So let me fly through this because we're running out of time, and I want to make sure that I can get to some questions, which you've already asked a ton of really good questions, everyone. I really appreciate that. So one of the things I mentioned is, sure, we try to simulate all the problems that could happen in space. And it's hard for us to like do things in space because we don't have, like, I can't go to work in space yet. I don't know if I'd want to, because it's deadly, and I'm not that, I'm kind of risk averse. So what we do is we try to like do as much, we try to create the environments here on Earth. And one of those things we've done, and I've done it before, is we take sometimes individual components or the whole circuit board, run the software on it, and then bombard it with radiation. We've done it here at University of Washington. I've done it at Texas A&M, and we use these cyclotrons. Or we actually go to hospitals because those, people get cancer treatment. We use that same equipment to send specific types of radiation and beams onto the electronics, and before we do it, we've already gone through a lot of expectations, like, well, what happens if it hits this part of the process? What happens if it hits this part of the board? What happens if it hits this transistor or what have you? And we try to predict the behavior, and then we test it to verify. We test and verify it here before we send it out in space. And like I said, it helps us identify those vulnerabilities before we say, yeah, let's send it, spend a few $1 million and blow stuff up. That's not always the best solution unless you're filthy rich. So, before I get into the next one, any other questions? Because now I'm going to go into like how you too can join the cause and help me make my job easier. Okay. So honestly, everything I've been telling you right now is just the #1 problem you deal with when you're trying to make stuff for space. You're always thinking about radiation. Like I said, in my field, it's more software and hardware. If you were in mechanical engineer, you think about off-gassing and how radiation actually can reduce seals and create different chemical elements and change the behavior of materials. That's a whole different field. I'm not going to get into that. But the thing is the same. We think about the environment in which we test and create our devices, whether they're code, electronics, mechanical, what have you. But once you understand that is the difference between how you make stuff on Earth and how you make stuff in space, all the other engineering techniques are the same. So really, what makes someone a good, or if you want to get into this field, you have to learn. You don't have to be born with it, but you just have to learn the right engineering mindset. And that means it's a combination, like I said here, it's curiosity, problem solving, and just always want to do something innovative. Not just disruptive, but just you just like, okay, what if this happens? Or what is causing that? And you think about the problem, but then you also think about how you can solve it, and then how you can prove that you solved it. That's engineering, period. So if you want to get into the engineering field, as long as you can think of those 3 core things: what is the problem? How's this affecting how I want things to happen? And how do I solve it? You'll be a good engineer. And then when it comes to space, it's how does radiation make my job horrible? How am I going to lose sleep tonight? Oh, it's radiation. Specifically, like I said, I'm an electrical engineer by degree, mainly software, just because I've been coding for longer than I should have. Um, it helps you understand how electronics work and how power works and how uh, things turn on and perform and behave. That's what an electrical engineering degree will help you get. Computer engineering is actually more where I fit, although back when I got my degree, we didn't have computer engineering because I'm old and stuff. But nowadays you call it computer engineering, so it's a combination of electrical and software or computer science. So it's you get you get the best of both worlds. I'm not saying just because I am one, but it's you get to learn about how you get to bridge the gap. You're expected to be more aware how those things work together, and you're also expected to be an expert at both. So then at the same time, be ready for that stress. Um, an aerospace engineer also has to know that stuff as well, but not so much they have to like write the code or they have to design the hardware, the electronics, but they need to understand the higher level concepts of like how do you get to space? What is space? What is fluid dynamics? How do you put things together? How do you create a rocket engine? How do you create a spacecraft? How do you test all that stuff? Aerospace engineering is just another level above it. And plus, like if you get sick and tired of doing space, you can just stick with the aero part, making airplanes. Um, Computer science is just hardcore coding. They're the ones who design the code that helps satellite even have awareness of where they are. I don't mean like consciousness, not AI, just knowing where they are, they've taken all the data from all the sensors that they might have. They have sensors that will tell you how it's facing the sun, how it's facing other stars, different constellations, where it is relative to the Earth. Because again, we don't have GPS in space. GPS is for Earth, not for space yet. So they're creating all these algorithms to help orient itself, how to move it in different locations in orbit, how to move it away from Earth, how to know when things are falling apart, but pretty much nothing but software. And and those are the core, at least within the context of spacecraft that I'm talking about. Those are the three main degrees that if you want to get into it, that's what you want to do. And bachelor's is good enough. Okay, you don't need to be a PhD. You don't need to even have a master's degree. I mean, I do have a bachelor's, but um, if I can get in there, you can too. And then you get to brag everyone and say like, "Hey, I'm a rocket scientist." Um, but like I said, the main thing is it's the engineering mindset. If you can understand that problem solving is what makes you an engineer, not a person who's just really good at writing code, not just who's really good at soldering stuff together or picking parts. It's not just the solutions, and it's not just being able to point out the problems. It's being able to help identify a problem, come with appropriate solution, validate it, and then send it. Um, as far as ways to get experience, uh, you know what? I do say here internships, projects, and research opportunities. Um, you know what? Fortunately, the internet is great nowadays. So there's just so many resources. I have a few on the next page too, but NASA um, pretty much shares all their information. So if you want to know how I do my job and you want to know about 2152 or documents, was it 8123 or something like that, the documentation that I use to help me follow a good engineering practice to make sure that what I say is doing what it's doing, or DO-178 or DO-254. These documents and these guidelines and these processes are out there for anyone to get access to. Um, uh, and honestly, you could still like if you want to write code, I mean, if we live in such a great age where it's so easy to get like you can install tools on any computer and even on your laptop, on your cell phones to start writing code and learn it that way. And even in electrical engineering side, you can buy a processor or a little, they call them a development board for literally $5. I just bought a whole bunch a couple of days ago, and it's so easy just to get started nowadays. And as a manager, I want to see that someone is going to say is actually looking into that kind of that technology and demonstrating that still that core aspect, which is that they're an engineer, but they actually understand some of those low level concepts, how to pick apart, how to write code for it, how energy, like how you power the part and expected behaviors, and then also the desire, that passion for innovation. So I don't want you just to say, well, here's what I can do, boss. No, I want to say, I want to know that that person cares about it, and they're like, well, what's happening next? And they're willing to throw out new ideas and so on and so forth. So yeah, like I said, I'll share the slide deck, but these are some core things. The two major agencies most of us pay attention to are NASA and the ESA, but there's Japan has one, JAXA, India has one, and my God, I just want to slide anecdote. When I was working at Blue Origin and India was making their first attempt to land on the moon, they're in the scientific and the space community. We are friends. We are buddies. We want everyone to win. And it was really sad when they crashed. But we all pay attention. We share as much information as possible because space is hard. We can't do it by ourselves. And we just it's a very inspiring field. It's like the most fantastic. There's like the two most fantastic things that us humans have done when it comes to science is go to space and probably undersea stuff, which we still haven't really touched yet. So just going to space is just the most amazing thing, and we'd love to share that amongst each other in the community. The last one is hardware manufacturers. We can't go to space without electronics that are meant for space, and so this is another way. You can learn more about radiation tolerant and radiation hardened processors, and these are the two major companies that we usually tap into to get our parts from, Microchip and Xilinx. I think that's it. Yeah. So any other questions, even random ones, even if they're not even related to space? Like I said, I used to work for Microsoft doing gaming, and there's still there are correlations between that work as well as space as well.
Basically, before you even go up, you need to make sure everything is tested, or you have to test it.
We should.
We should.
We should.
So it's not always. Don't test like with the NASA, like she was saying, they to check everything and halfway up there, you know.
So
Isn't that like that could be critical to people's lives? It's not just about the machine itself, it's taking lives.
Yes, testing is important. The catch is we're doing things we've never done before. And we can only try to test as much as we can possibly humanly think of. And we're going to miss stuff sometimes. Like no engineer who worked on that project said and walked away. The engineer who actually tried to push them to check for it, that man he experienced significant trauma for the rest of his life because of that. So it's not like people are out here just like, send it. We don't talk about those people. They're not really involved. Or there's a much louder team of folks who are saying like, we should check it. But when mistakes happen, they're mistakes. They're not intentional. They're not, I want someone to die, unless it's espionage, which I'm pretty sure that wasn't the case. And that's not a thing that happens back then.
No, I don't think that. I mean, no, I don't think that was real. That's not what I think.
It's really not apathy and it's not indifference. It's just in order to meet that launch window, and the launch windows vary. It has to be just the right wind speed, has to be just the right temperature parameters, has to be just the right weather, has to be just the right position at the target. If they were to basically, through paranoia, go and remove all of those O-rings to double check for a problem that probably didn't exist, they moved the launch window back, they missed that launch window, and we have to start the whole process all
There's always the balance of time, cost, and efficiency and stuff like that. But then we're very data driven. We're not emotion driven. So paranoia is not good enough. And like I was telling you, with the systems that have like the minimum 3 for the voter system, and hardware, we call it triple modular redundancy. Even in those cases, you still might have that one that differs, but we're using a paradigm that says, well, we still have 2 that say it's okay. That third unit isn't going to go back and say, well, I told you so. It's just a mistake. So I just want to say that because that's just the very common thing that happens in the engineering world. We don't place blame. It's horrible. Like I almost didn't want to be in space because of that. I remember that. I actually have a journal entry when I saw the Challenger explosion occur. It had almost made me not want to get into space. And we don't not think about, that's the right double negative, about the ramifications of what a mistake could be, but they're mistakes. And so we have to live with it. We know some people might lose their lives because of it, but in every single step of the way, especially this phase of space exploration and travel, and we're all willing to make those sacrifices. Like if someone said, Emile, you have the opportunity to be the first person to orbit Venus, and you're the only person that did it, or could do it, or go to Mars, or what have you, and I get to further humankind, yeah, I'm gonna do it. I may never come back from it. I might have serious radiation poisoning. I might have lose bone loss, but it's that aspect of it. So I just want to put that out there because we're really sensitive about that because it's because of all the testing we do. And sometimes one thing gets past us and it wasn't intentional. It's not incompetence. It's just, we literally have billions of parameters we're trying to analyze. And the fault tree analysis, yeah, it's so complicated. Fault tree analysis, fault hazard analysis. If you saw the trees and the literal millions and billions of combinations that we go through, and even when we see that one anomaly, we're still saying pay attention to it. And so the billions of transactions, the billions of calculations, one anomaly, still someone saying let's pay attention to that one, and there's another one that may not even appear as an anomaly, pops up. Again, it's not due to we didn't try, we did try.
And
Trust
some
me.
things just can't be tested. The moon landing, 1969, the Sea of Tranquility. There was no way to test whether that was going to be a solid surface or 20 miles down the powder.
Mhm.
There was no way to test.
Yeah, dust is a horrible, trust me, like I said, I designed the landing engine for Blue Origin. Dust, just the dust that comes up when you're landing and the fact that it could be ingested as we're doing a throttle descent is like, it's mind blowing.
I mean, those men had ice water in their veins, not blood,
Yeah.
ice water. They knew the risk, but there was no way to test it.
Yeah. Okay. Any questions from folks online?
Real quick, for those of you guys who are online and registered for the course, please make sure that your full name shows up or respond to my message in the chat so I can log your attendance.
Anything, anybody?
Any other questions?
Let's see here.
Okay, I don't see any additional questions. Like I said, there's two folks in the Zoom room that I sent a direct message to. If you could get back to me, that would be fantastic. Otherwise, thank you so much for sharing your work with us.
Welcome.
Thank you. When you talk about the corrections part, you said some things fail, but they'll correct themselves. What is, even though you can't test everything, what would that? You said like when it comes to the zeros and the ones, some things they can correct them.
Something is projected. They're not like,
Oh,
it's not like, it says, oh, I'm supposed to be a one. No,
Oh.
there's, so. So. We have memory. For the story. Typically for space, but also in, like, say, servers, things that happen in the cloud, there's something next to it that actually stores a signature of sorts. So it's like it says that this is what we think, this is how it works. Let's say you have a piece of data that says 0, 0, 0, 0, 0. But then next to it, there's another set of values that are associated with that number. It's like the signature, it's like a special code associated with that. So then what happens is every single time that piece of data gets changed or read, there's another process of looking at that signature.
okay.
And that signature is another way of representing the one. And if that signature and the data don't match, then it says, oh, something's wrong. I've detected an error. Because of, so it can at least do the first part, the detection phase, but then after that, there's a potential correction. So usually we call it is, the term is SecDec. It's a single event, single error correction, level of error detection, or something like that. I forget how. What that means is that if there's a single value, if one of those zeros or one is not the one or the zero that the signature is telling us it should be, if it's just one thing that's off by, that same thing that's like checking it, you can also say, oh, office. So again, nothing's happened by magic. There's always something else on the side
Okay,
that's checking. So, oh, let me fix that.
okay.
But if this value over here is like a whole bunch of zeros and ones that's not supposed to be there, the signature will still say that's not the right value, but there's just too much crap happening over there. And then it'll signal us to say, yo, that I don't know what the heck that is. I know it's wrong. I can't fix it. So what are you gonna do now? And then that's where I have to write these as well. I skip it. I can try again. I can try to find another way to correct it, or I can say, screw it, just restart the whole thing, but we start just part of the code. There's all kinds of things. That's where all hazard detection, all like
So it depends. Okay, thank you.
Well, I have to catch a flight,
Oh.
so I am going to close everything up. Thank you again for attending my seminar. And we will see you guys next week.
Thank you very much.
Thank you.
Have a safe flight.
It's like, where you going?
I am